before of advent of code. Uh, it's not really a reflection of the difficulty of the problem, just the approach I wanted to take to try to solve it, which is to decompile, or not really decompile, do symbolic execution on the simulated ALU that's part of the problem. So unfortunately, my last stream got cut off. Still only the first 7 minutes. So what I've been doing today is writing some correctness proofs of the transformations I make on the abstract syntax tree I've created from the raw instructions. So we build up a tree of what the value of each variable is in terms of the inputs and constants. And we can simplify that doing things like removing identities, and then f star is able to prove that that's correct. So what that means, so I had to write a function to evaluate expression for any given set of input values. And what we want to ensure is that if it evaluates correctly, if it doesn't do division by 0 or modulus by 0, then the value as originally given and the value of the transformed one are the same. So you can read this as for all expressions and for all input values, if the expression evaluates correctly, then it will do so both with the same value both before and after the transformation. And this is an easy one because f star is able to just work through all these cases and say, yep, I agree that's true. Some of them are a little more difficult. So here is the code that does constant folding that converts multiple additions into a single addition. And so we have to mirror the structure of that function in the proof that it's correct. And mainly this is just a proof by induction, but it has to handle all the different cases. And so the really tough one is these simplifications of division and modulus operations. So if we multiply by something and add a small value and divide, we get the original value back. Or if we multiply something by a number and add a small value and take the modulus, we get the value we added back. So those are fairly simple to write as transformations, but the correctness proof is about twice as long. So this first one has a bunch of extra assertions because I needed to figure out what I needed to add. But basically, this is, again, paralleling the exact same steps of the proof and of the original function and showing that we get the correct result in each one of them. So it's a proof by cases rather than a proof by induction. So to do this, we just need to, extract the values. We need to call some f star standard library lemmas about what does division do, what does modulus do, and f star can figure out the rest from there. But it's, like I said, it's significantly longer than the original proof, than the original function. So the other thing I did in my code is structure it so that rather than being the equality operator, which is what's in the original ALU, I introduced a new expression that's an if-then-else clause. And everywhere we see a equality, we either put in a literal if we know what the equality is already, or we convert it to this. And so what I'd like to do is prove the correctness of this very general function. But the problem is this function here is very general. And so the place I got stuck before I quit for the afternoon and went and had some tea. I've got some more tea now to fortify me. is I was just trying to work on one of the cases. So either my lemma is not correct or I need to do more work to prove something about what form this function may have or place additional restrictions. So the problem is if we know that we don't do division by zero, let's think about division by zero is the only thing that would cause us to not be able to evaluate the expression. If we can evaluate the original one and we can evaluate each of the arguments, that doesn't mean we can swap in another value and still guarantee that it terminates. So, this assertion here is what's failing. That the transformation we do is move the operation further down the tree of if then else statements. But how do we know that this operation, whatever it is, applied to T1 and to this is B is arg2 in this case. I should have given it the same name, but the pattern matches B, but it's filled with arg2. How do we know that that still produces something that fails, right? Op could be this arbitrarily deeply nested function that, calls division by zero every once in a while, but just not on arg1 and arg2. And so I'm not really sure how I'm going to fix this. In reality, this is just called with the constructors of the type. So one way to go would be to say, well, instead of an arbitrary function, we'll take one of a list of functions and we'll prove the property we need about just everything in that list. So that's one way to go, is say, well, add op behaves nicely and multiply behaves nicely and division, as long as the second argument's not zero, that's fine. And same with modulus. And I think that may be the only thing that works because, again, we just specified some arbitrary expression. The other thing we could say is, put a refinement type on this function to say, well, it doesn't return an arbitrary expression. It returns an expression that is well defined whenever the second argument is non-zero. But even that might not be enough. It might cause a lot of trouble. But I think, and the third option is just stated as an assumption. They say, well, assume that it works out, and the proof will be conditional on that assumption. So that's probably the cleanest way. And we could even write it in as one of the requirements. So we could say that okay, so what do we actually apply the operation to? I mean, the other possibility is this is actually incorrect in that case, that we push something past a check for equality so, but I don't, I don't think we have an error of that sort. But I did earlier today run into a transformation I was doing that was incorrect, and when I tried to prove it was correct, F* kept giving me errors. So I eventually decided it was a simple math mistake, and Modulus didn't actually work that way. Right. So if we like think about this case, T2 could be 0, or F2 could be 0, and when we push the op down, we're doing division by 0, where we previously weren't before. So maybe what we need is to say we assume that the result runs without error. And that might be something nice to prove, that we're not introducing an error, but we could maybe do that as a separate pass if we wanted. So let's try that. So we'll just, so we just encode that as a requirement is, when we evaluate the expression on the set of inputs, it runs without errors. The proof only applies to the cases where that is true. And we might have difficulty proving that, but for this lemma at least we can do it. So does that help us with our assertions? No, so it can't prove the precondition. Because again, I think it's too strong. It doesn't know what operation we mean. So let me think. So we could just prove this for a particular operation. Let's try that first. And see, then we can look back and I'm actually going to remove this. All right. All right, so that works. It says, okay, that's just induction. If we inductively assume that the base case is correct, then this case is also correct. And this one should be trivial. Can figure that out for itself, I think. I guess not. Because we've got all this crud. So what we need to do is appeal to our proof that the simplification function we call is correct. So Okay. Okay, so part of the problem is I call simplify identity first. I'm not sure I need to. Yeah, I kind of need to. Because I want to. So the thing we don't know about that function is it won't transform and add into something else. That's not something I've proved about it. Maybe we can prove that though. Okay. Okay, so we assert that that returns an add operation. I don't know if that works. We should probably use our simplify identity correctness to say, okay, whatever it does, it won't interfere. Simplify. Okay, we need to specify. We always need to specify the set of inputs as an argument, and it really, you wouldn't call this with a particular set of arguments. It's just acting as a for all. Okay, but then we need that. So I think. Oops. I made it unhappy. think that's all we need for our base case here. You can sort of tell when star is taking a while. That doesn't necessarily agree. All right. Does that assertion actually matter? It does, because otherwise you have to prove that the things done in here are correct, which we're going to have to handle anyway at some point, but I was hoping to do this. All right. And it's not really true, right? We could add two literals and end up with a literal. All right, so what we really care is that it is not an equality operation when it comes out the end. All right, that seems like something we could prove. All right, so we've got a pair of expressions. I don't think we need anything about them. All right. So what do we need to do to prove it to them? Oh, okay. So, I mean, if we add 0 to an equality, we end up with an equality. Well, all right. That kind of sucks, but let's just bite the bullet. Okay. All right. All right. So let's handle the easy case and the hard case. Good. All right. So the easy case works, where if it's not equality, then we just use the lemma we've already proved above about the next transformation we do is correct. So I think my proof here is not strong enough. You notice this is another one we could get. So I'm proving that if this returns true, then if it returns true if and only if the value is 1, but we need to specify the value is 0 when it's false. So we can do that as a pair of implications. So make that one way, and if it's not true, then it's 0. All right, can it still prove that automatically? It can. All right. All right, so we're converting this equality to, I think we need a nested match here. Again, we just need to all right, so I'm really hoping it can prove this case by itself. And if it can't, if the equality is not known to be true or false, then we just convert it to something that should be the same when we evaluate it. And if it is known, then the theorem I just corrected, where'd it go? Says that, hey, when you evaluate equality, you get 1 or 0. Which is what we wanted to establish. Oh, I need to give it that. All right, let's try that out. Hey, it worked. All right. So this case is just the mirror of this case. Let's try that out. Okay, good. And so now we have the most complicated case where we got both operands are if-then else's. We want to push down both trees. Okay, so what we do here is if true and false are identical, then we can just elide the if-then else. So again, I think we just mirror the code. So hopefully, we may need another lemma. Hop to I'm not feeling so good about this. Not because I believe it's false, but so these all need IVs on them. And we need to group these statements. Otherwise, the else statement only takes the first one. All right, and this only applies to. Right now, we're only doing the proof for addition. Oh. All right, interesting. So it can't tell that adding corresponding values results in not an error. Okay, so what we need to do is we need to only look at the true values when the condition is true, and the false values when the condition is false. Let's try that and see if it gets further. I mean, we got the same problem here. Okay, so if they're both true, I think we've given it everything it needs, but in this case, it should be that I think that's a true statement. What's it complaining about? I don't get it. Option int is not a subtype of expected type function to function with no types available. I don't know why it's expecting that type. That is a valid expression. We just have that up here. Unclosed parentheses somewhere? No. Oh, there we go. We're missing the... It was comparing us to a function type. Okay, why doesn't it... It should be the case that this proof is getting too long, but I don't know a good way to split it out. All right, it agrees that if x1 equals x2 evaluation, then y1 equals y2. That's good. So why does it think... Oh, all right, I got the variable names wrong. I was comparing this to this, but what I wanted to do was compare this and this, which also compares x2 and y2. All right. I think I switched conventions somewhere along the line, and that is what confused me. Okay, good. So it got through that case. We just need to do the same thing here. There may be a problem here. that these are equal, but they could be equally none, in which case the value would be none. But I didn't run into that problem in the first half, so okay, good. So how do we generalize this from add to other operations? It may be that the problem wasn't with the operation at all. It was with this check here. All right, let's copy that and try to generalize it from addition to any operation. All right, so why doesn't it think that is the case? So we know arg1, arg2 is well defined. Arg1, arg2 are if then equal to. So it should be the case that I think this should be the case. All right, so this is trivial. I'm getting an idea that it might be because this is an operation on expressions, so it could do why. All right, let's say something that's actually true. All right. The idea I'm having is that the property we need from the general operator is that it doesn't introspect what the expression actually is. Its value only depends on the value of the operation. So it's sort of a well-formedness, not really well-formedness. It's a structure independent operator. which all of our constructors are. They don't care what's the argument is. So can we write that as a type? I think so. All right. So type constructor. So it's a function from so we want to say is for all expressions A and B and all input vals, the evaluation of FAB is equal to if we just applied F to the literals. Except, all right, so we may have to get more fancy yet. We may have to say when we can evaluate both expressions. All right. All right, whenever we can evaluate both expressions, then we can substitute in those values to F. All right, so that's a fairly complicated type. Does that even type check? No, because we missed that. All right. I have my doubts about whether, I mean, that's the property we want. Is I have doubts about whether f-star is going to be able to work with that, because we certainly didn't give that as the requirement here. But let's give it a try. All right, so we say op is of that special type. We still failed in the same place. So yeah, I don't know how we're going to generalize. So one thing is we could just write the proof 6 times, once for each operator. It's kind of silly. I'm just gonna slap an expect failure on this, because we did prove it for add. I don't have serious doubts about its ability to work for the other operators. All right. So right now the code just prints out the possible zeros. So we get a list of, unfortunately they are all actually zero, they're not just, so we get a set of conditions. And so what I'd like to do is now walk this set of conditions and come up with a set of inputs that validates it. And fortunately, we sort of know that each one is only going to refer to values that appeared. We're going to introduce a new value on the right, and we're going to only use values that have been previously done. And to do the maximum in lexicographic order, we want to make each of the new ones as big as it can be. So let's try this. So okay, so we're going to take a list of conditions. They're going to be list of bool, expression. I'm going to do ML so we can fail here if it's not of the expected form, which is that there's I guess here we introduced a new variable and didn't put any conditions on it. Okay. And rather than doing something fancy, I think we could just cycle through any unknown ones. It's this one where we introduce two variables at once that causes me problems. And we do have, this does have some dependency, right? This means I2 cannot be 1. And there's similar constraints here. So this is not as, right, like this says I0 plus 7 mod 26 minus 4 has to be 1 or greater. Well, and it can't be greater, it can't be too large either. Okay. Like if I0 was 9, 16 minus 4, 12, it would be too big. So I guess the easiest way is just backtracking, which is kind of silly because we could have done that at the very start of the problem and avoided all this breaking things into cases. So I really would like to find a way to use the information that we've got here. I guess the advantage is we don't have to evaluate all the code, and we don't have to, we can terminate early if we meet an unsatisfiable condition. All right. So we're going to go until our list of conditions is empty. We can drop things off the front if all the variables in them. Gosh, we need a lot of work to make of work yet. Like we don't have anything for saying is a variable referenced in this expression. Which is a shame because it feels like we could pass these to the SMT solver and it would, I guess it doesn't do maximization, but it would tell us whether they are satisfied if we could just encode it correctly. Well, so the easy things we could handle, right? We could. This is becoming this is really becoming rather complex. The easy additions we could just handle. We could do a special case for them and say, oh well, in this case we don't need to evaluate it. We just need to set them up Set one based on the other. I guess that's the other way we could look at it, is say, well, previously we've got all possible values for all the variables. So we've got sort of a set of values they could be. And then we could shrink the range by sort of taking multiple passes through this and saying, okay, well, I kind of like that as an idea. That might be simple enough to do, right? We could say, well, based on what we know now, could I0 be 9? We'd run through these, and everything else is unconstrained, so it's basically just looping through, though. And what we need is a data structure that lets us say, I seem to be talking myself into building a SMT solver on top of F star, and that's wrong. If we're going to do this using a SMT solver, we might as well just encode it as a Z3 problem and give it to Z3, which I'm not going to do either. So let's all right. I'll take the input number. Vals. Okay, so we're just gonna set them in order. We're not gonna try to be clever and do it opportunistically. We've got the list of conditions we need to satisfy. And we're trying to add one value, the largest possible value, to the tail of the values, as long as it's less than 14. And we return the input values. All right. Oh, and we need, what is our candidate value? Just gonna call it N, gross abusive notation, so. I feel like we need some way to signal, did it succeed or did it fail? All right, so what are our base cases? So if the length of the values is 14, then we did it. So otherwise, we're going to try n. Okay, that causes a problem. So we really should only try the ones that have the variables we've already assigned. Okay. So I guess we're ending up writing this anyway. Yeah. All right. All right. So all right. So we're going to say, hey, does this only use inputs up to and including the given number? And so we got to walk our way through our expression tree. That might be a better example. We should have copied. All right. If there's a literal, it's just true. If it's an input value, then it's got an index, and we return I is less than or equal to input num. And all these are of this form. Multiv mod equal. All right, so we can actually collapse those. Like that. And then so I mean, this really should not happen, but we're fine. We'll just okay. So we want to filter the list of conditions to those that only use the variables less than or equal to the one we're trying to assign. Okay. So we're going to do Okay, so we're filtering out okay. No, we need to do better. We need to, okay, so we take a pair, a triple actually. Can we do that? I don't know if we can do that. All right. All right, so far so good. Fixed all the little problems there. I've been using the wrong return. Been using input vals, which is a type, as the return value. Okay. All right. So does it work? All right. So if for all of our pairs, good old value expression x. All right. If they're equal, supposed to be equal, then if they're equal, then equal. All right. So this is more general than we need to be because the right-hand side is always just a variable, but it doesn't hurt, I think. All right. So all right, so every condition that we tried worked with the value we assigned. So let's go on and do the next variable, but that might fail. We might have to backtrack. So we call it, but we match it to see if we got back none. So give it the attempt, reset n to 9. You don't need to explicitly use a length, that's fine. Keep the same conditions. All right. If that succeeded, then hey, just return the success back up. Otherwise, it failed. So if it failed, then if n equals 1, we can't try any smaller, so we got to fail. Else try largest input attempt n minus 1 conditions. Oh, no, not attempt. Because attempt is the one that's expanded. Vals. Okay. All right, we do the same thing here. All right, if n equals 1, then we can't go any smaller, otherwise keep the same value, but try one smaller number. All right, you made the interactive session unhappy again. That happens a lot. Sometimes we've got a syntax error, but not always. Now let's go in and reevaluating all our previous statements, feeding them back into the interactive session. There is a way to save some information so that it goes faster the next times, but not in the... Hey, all right, so that type checked. Let's try it out. All right, so match largest input, empty list, start at 9 on the list of conditions. Oh, all right. So fstar does not, among the many things it does not have, is a nice way to print out a list. So we got to write that too. All right, if it's an empty list, don't print anything else. If it's a head followed by an empty list, then just print that head with nothing following it. If it's a head and a tail, then we're going to print a semicolon in and a space. All right, we got to put the parentheses in so the nested matches are unambiguous. And let's give that a try. I don't have a lot of confidence in that searching function. It seems like the sort of thing that's easy to make a mistake in. Yeah, it says everything's unsatisfiable. Kind of doubt that that is the case. Oops, I didn't want Firefox. Well, when all else fails, can go to Printf Debugging. Fortunately, a lot of the things we'd like to print don't have their own print functions. All right, well, we just wrote that. So So this record hints and use hints is what I was talking about earlier. That oops, there we go. Oh, this isn't right at all. Okay, yeah, that's better. Oh, what was it complaining about? F star types are not covariant. So a list of a refinement type is not a list of the base type, but there is a function that makes it so, which actually just compiles down to the identity function. So I think there would be ways to write my print function so it could operate on any refinement type, but it'd be a little more complex. All right, let's take a look at this. Did I not filter? We made some progress on that last one. All right, so there should be 0 applicable constraints. So we're doing 0, okay. So this needs to be strictly less than. Or no, let's do it this way. I'm happy with that. So the first input to it should be 0, which is the length of vowels, not the length of tempt. Yeah, so, and off by 1 error. Okay, that looks more sensible. All right, so this is true. So 19, no, okay, 9 plus 7 is 16, mod 26 plus 11. So yeah, there's basically nothing is gonna work on that one. Boy, we're doing a lot of redundant work. We should be really nice to continue our symbolic execution approach and say, like, this is always going to be. We should be able to do that. We should be able to look at a condition and say it's a modulus plus 11. It's never going to be equal to a variable. I already did that for plus. Let's thought. Yeah. So we need another clause here. On anything. Okay, so no, we do need the input value. All right, so this is going to be. Oh no, we need to go another step further. All right. It's a very complicated pattern, but that's okay. Literal. On 26. All right, so that's the form we've got. It's maximum. All right, so how do we decide whether that's impossible? So the lower bound is 1 plus k. The upper bound is 9 plus k. So if the upper bound wraps around, then we've got more work to do. But if it doesn't, then y has to just say we don't know for the hard case for right now. Okay. So LB plus Y so So this is an interval. This is an interval overlap problem, which we've done before in Advent of Code. So LB plus y less than or equal to 9, and it feels backwards, but that's what the math says, right? One. If LB plus y is greater than 9, then we're out of range. And if the upper bound is less than 1, then we're out of range. And if neither of those, if we're not out of range, we have to be in range. So can we handle this other case? All right, can we prove this is correct? Well, this lemma still does not work. Well, it could not work because it probably doesn't work because we got that modulus in there. All right, match. All right, so let's just handle, let's try that out. All right, can I handle everything but that case? Yes. So that's a case that's given us problems. All right, so come to think of it, we wrote a bound. Okay, we only handled addition. Yeah, that makes sense. All right. Just make sure we're on the same page here. good. Okay, there's a problem. That could well be a bug, but I think we're gonna have to use the lemma about moduli here. Okay. All right, how are we doing so far? Okay, good. All right, math.lemmas small mod. Modulo is P26. And so both those mod 26 are themselves. We may actually have a bug. So if lower bound less than 0, go. We could wrap around the other way. Okay. So it was telling us about a bug. I don't know how much of this actually was necessary. I kind of still think it was. At least the lemmas. Yeah. All right. So let's put in just that. That is nope. Oh no, I broke it. I broke it. Or it might just be inconsistent. What else do I have that admit in there yet? I did. All right. It was an illusion. I wish it would tell me which case was failing. It just knows it hasn't got there. So the poor man's way of doing that is just throw admits everywhere. Well, we already require that is equality known is true. All right, so we know we must be in this case. So all right, so why doesn't it think that is true? Oh, it's the wrong type. Oh, okay. We're in the case where it returned a known. It's known. The only way we can do that is it says false, so it should be that LB plus Y is greater than that, or So it's less than LB plus Y, or it's greater than upper bound plus Y. Something's wrong here. Did I reverse the logic here? Let me look at this again. Oh, I said and. So if the lower bound. All right. Okay, so cannot happen if I got this backwards. I wrote when it can happen. If lower bound plus Y is too big, or upper bound plus Y is too small. Okay. Bound plus Y greater than 9, or all right. So how much of that? Yeah, even that might not be necessary, but we'll leave it in. All right. Yeah. Well, when having trouble finishing a proof, go back and check that the code's actually correct. All right. So this should actually remove a bunch of cases that are simply impossible. All right. Well, that looks better. I think that might be our solution. there really only one? All right, let's dump all our Huh. That is very interesting. There is only one number that works. Well, let's plug it in. And see whether that's right. I mean, 659. Oops. 659-849-1999-7939. Wow. Hurrah. So there's definitely a bug here. Oh no. It's exactly the same condition. All right. So there's only one condition that's satisfied, and I found the largest value for it, and I need to just find the smallest. And that is just changing n+1. Start the attempt at 1. Change this to 9. Looks right. And length started at 1. Okay, so all the work I put in showed that there's only one case where we get a 0. And so our search problem is limited to just that case. And we're doing brute sort for search, but only on that case. So 11984919547. Just a little surprising. Well, it still says it's too high. So probably a copy and paste error. Or a bigger program problem, a bigger error somewhere else that there really is another condition that is satisfied. Oh, did I just, no? Oh, okay. Yes, it was a copy and paste. I recursively called into largest. All right, that's the danger with copy and paste. So we probably don't need those. All right, that looks better. It may not have been a minute though. 112.116.195.41713. Hurrah! All right, we're done with day 24. And we probably got a very poor, well, we're the 9600th person to solve it. Could be worse. All right. Well, I'm very happy with where we ended up, even though I made a silly mistake. So, yeah, I'm going to write up my notes. I'll push this to GitHub. Merry Christmas to all. And as you can see, I've still got I've still got 3 stars left. I haven't solved an F star. Day 17 is sort of similar to this. There's an easier way to do it, and I'm just being ornery. I want to have F star prove that the search is in the right area. And similarly with 8, it's a logic problem, and so I feel like there should be a logical proof, but F star is making it difficult to reason about finite sets and permutations. But probably I will tackle at least part of those in later streams. So good night.